Gazing down from space, we marvel at Earth's bountiful oceans, its continents, and its life-giving atmosphere. It looks so peaceful, so perfect. But what if I told you that our world was born in a fiery, violent cauldron of cosmic chaos? Imagine a time when gas giants stirred up destruction, and a young, unstable sun vented its rage. How did our planet begin? And more importantly, how did Earth survive against all odds to become the paradise we know today? The story of Earth starts over 4.6 billion years ago, deep within a giant spiral galaxy, the Milky Way. At 100,000 light-years across, our galaxy is a cauldron of swirling dust clouds and glowing gas. In a cosmological blink of an eye, millions of massive stars live and die in powerful explosions known as supernovae. These violent flashes of light aren't just destructive, they are the ultimate creators. They seed the cosmos with the very stuff of planets, carbon, silicon, iron, and more. One such explosion packed enough punch to send a nearby giant molecular cloud of stardust into a gravitational collapse. This cloud, likely located at the edge of a Wolf-Rayet bubble or similar to the Orion Nebula, was about as cold as the universe gets. But as gravity pulled huge volumes of dust and gas into its core, it began to heat up. A storm erupted at its center, a vast, raging hurricane of dust, gas, and ice crystals. In the eye of this storm, temperatures soared, a star ignited, and our sun was born. The newborn sun was being fed by a slowly spinning disk of pre-planetary matter. This spinning protoplanetary disk was the cradle of our solar system. Within this disk, planets began taking shape in a long, violent process called accretion. It started with microscopic dust gathering into sand-like grains. Over millions of years, gravity drew these pebble-sized objects together to form rocks, ice balls, and boulders. In the inner solar system, the region inside 4 astronomical units, AU, it was simply too warm for volatile molecules like water and methane to condense. Because of this, the planetesimals that formed here were built from compounds with high melting points, such as iron, nickel, and rocky silicates. These objects coalesced into miniature planets, or planetary embryos, which grew through constant collisions and mergers. Slowly, over the course of less than 100 million years, this brutal demolition derby gave rise to the terrestrial planets we know today: Mercury, Venus, Earth, and Mars. Further out, beyond a boundary known as the frost line, the environment was cool enough for icy compounds to remain solid. Here, planetary building blocks were much more abundant. This allowed the giant planets, like Jupiter and Saturn, to grow massive enough to capture vast envelopes of hydrogen and helium gas. But Jupiter wasn't content to just sit in the outer solar system. It was about to embark on a journey that would profoundly shape the destiny of our young Earth. Scientists have used supercomputers to model Jupiter's rise, and what they discovered is known as the Grand Tack Hypothesis. As the giant Jupiter grew, it succumbed to the gravitational pull of the inner solar system and began to spiral toward the Sun, much like a sailboat changing directions to tack into the wind. Jupiter's Grand Tack brought it all the way into the orbit of present-day Mars, around 1.5 astronomical units. Along the way, this massive gas giant ploughed through clouds of cosmic debris. What it didn't swallow, it flung out of the solar system, severely reducing the mass of the inner solar system and stunting the growth of Mars. Fortunately for us, another giant planet, Saturn, grew large enough to capture Jupiter in an orbital resonance and pull it back out. But Jupiter's violent migration did us a massive favour. As it moved through the asteroid belt, it scattered water-rich, primitive, icy asteroids inward. These cosmic ice balls were left in orbits crossing the terrestrial planets, providing a crucial mechanism for delivering the massive amounts of water that would eventually fill Earth's oceans. Earth, at that time, was a roiling embryo of the planet it would one day become. It harboured volcanoes on its surface and possessed a thin, toxic atmosphere. It had survived the onslaught of planet formation and the chaotic gravity of Jupiter, but it was about to face the ultimate test of its life. Another protoplanet, roughly the size of Mars, was closing in. Scientists call this doomed world Theia. About 4.5 billion years ago, Theia bore down on Earth, delivering a cataclysmic, glancing blow. The impact sheared away a third of our planet, rocking Earth to its very core. Debris unleashed by the collision enveloped Earth in a dense atmosphere of vaporized rock, forming a belt of molten rubble. Much of this orbiting debris rained back down to the surface, but within a century, the remaining fragments gathered together to form a single wondrous body, Earth's companion, the Moon. The birth of the Moon was a blessing in disguise. Following the impact, Earth was left spinning rapidly on a tilted axis, but the Moon's gravitational drag eventually slowed our planet's spin and steadied its tilt. This stabilization was vital. It prevented Earth from wobbling wildly and paved the way for the balanced, regular seasons and stable climate necessary for life to emerge. But the violence was by no means over. Between 500 and 600 million years after the formation of the solar system, a period known as the Late Heavy Bombardment began. As the outer giant planets shifted their orbits, they threw the asteroid belt into chaos, sending a massive barrage of asteroids and comets hurtling toward the inner planets. These impacts carved huge basins into our Moon and repeatedly pelted the Earth. Yet, against all odds, Earth endured. It had secured a heat source, a magnetic field, a stabilizing moon, and the precious water delivered by cosmic impacts. The stage was finally set for the greatest miracle of all. 500 million years after the birth of the Moon, the intense bombardments finally began to subside, and Earth had transformed into a world of water. Its seas spanned every horizon, broken only by jagged, dark volcanic islands. The Moon, still in a much closer orbit than it is today, whipped up massive tides that violently lashed these rocky shores. Earth's atmosphere was a thick, unbreathable mix of hydrogen, nitrogen, and carbon dioxide, heavily laced with water vapor. The planet had gathered all the necessary chemical ingredients, carbon, nitrogen, oxygen, and iron, to accomplish its ultimate feat, nurturing life. But Earth was facing a quiet, invisible crisis. Its precious water was slowly disappearing into the void of space. The young sun, though dimmer than it is today, was incredibly volatile and prone to powerful solar flares. When these intense solar particles struck Earth's upper atmosphere, they blasted water molecules apart. Lightweight hydrogen wafted away into space, while the heavier oxygen sank to the surface and bound itself to rocks. We know exactly how devastating this process can be. Just look at our planetary neighbours. Spacecraft observations reveal that Mars once harboured ample stores of water, complete with meandering rivers and deep oceans. Today, Mars is a barren, lifeless world, with a painfully thin atmosphere, stripped of its water by solar radiation. Venus suffered an even more hellish fate. Stripped of its oceans, Venus was left with a witch's brew of noxious chemicals and thick, sulphurous clouds. The buildup of carbon dioxide trapped the sun's heat, turning Venus into a highly pressurized cauldron with surface temperatures of almost 500 degrees Celsius, the hottest planet in the solar system. How did Earth avoid this grim, scorching fate? Our planet possesses a hidden, protective shield that both Venus and Mars lack: a powerful magnetic field. Generated deep within the planet by the exchange of heat between Earth's core and its crust, this magnetic force field deflects the most dangerous and powerful waves of radiation the sun can throw at us. It is our planet's first and most important line of defense. But Earth's second line of defense began to simmer across the surface as early as 4 billion years ago. That defense was life itself. While no one knows exactly how or where life gained its first foothold, long-standing theories point to the stirrings of undersea volcanic vents, or hot springs dotting the landmasses of early Earth. Here, heat and chemical reactions over millions of years produced proteins and nucleic acids, the fundamental chemistry of life. Life emerged, but it truly began to spread thanks to a revolutionary biological breakthrough: the ability to turn sunlight into energy. Over 3 billion years ago, simple bacteria developed a process called photosynthesis. When a photon of sunlight passes through the transparent membrane of these bacteria, it hits special spherical pods equipped to harvest solar energy. This light excites rings of chlorophyll molecules, and the energy is transferred across a family of proteins, the tiny machines of life. Protons stream into watery spaces within the cell, and as they enter, their electrical charges literally turn a protein structure like a mechanical crank. This microscopic turning motion joins two molecules together to form a third, called ATP. ATP is the universal energy currency in every cell that has ever lived on Earth. Acting like a biological battery, ATP stores captured solar energy in a stable form, allowing the cell to break down food, move, reproduce, and flourish. As bacteria evolved into plants, an advanced form of photosynthesis released a miraculous byproduct: free oxygen. This new supply of oxygen flooded the atmosphere, where it bound with hydrogen to form new molecules of water, preventing the hydrogen from escaping into space. While Earth still ultimately lost up to 25% of its original water stores, life had successfully stemmed the bleeding. Across the surface, water, life, the sun, and geology began to work in perfect harmony to power a remarkable planetary engine, the global climate. Earth's climate is driven by the uneven solar heating of day and night, alongside ocean currents that mix cold, deep water with warm surface water. But what keeps the planet from overheating like Venus is the presence of life itself. The oceans are chock full of microscopic phytoplankton. These tiny organisms take in atmospheric carbon dioxide and send those carbon atoms on an incredible journey up the food chain. Phytoplankton are eaten by zooplankton and tiny crustaceans called copepods, which are then eaten by small fish, and eventually by the largest creatures on Earth, like whales. From tiny phytoplankton to massive whales, marine life removes CO2 from the atmosphere. When these plants and animals die, this carbon-rich matter sinks all the way to the sea bottom. Over massive timescales, these carbon sediments are crushed into oil or rock, such as limestone. The Earth only releases this stored carbon when rocks become exposed or when volcanoes erupt, spewing over 100 million tons of carbon dioxide back into the atmosphere each year. This delicate, millions of years long carbon cycle has kept our planet habitable, and its ultimate success depends entirely on life itself. Today, Earth is endowed with bountiful oceans, a protective atmosphere, and life that is perfectly in balance. When we reconstruct our planet's past, we realize just how many miracles it took to achieve this paradise. We survived the violent aftershocks of supernovae, the devastating gravitational pull of Jupiter's Grand Tack, a cataclysmic collision with another planet, and the brutal stripping of our atmosphere. Our existence is a wondrous twist of fate, a remarkable convergence of chemistry, energy, and sheer cosmic chance. Our planet became a paradise, but as we look out into the endless starry night, we have to ask ourselves, is it the only one? If you made it this far, thank you so much for joining us on this incredible journey through the birth of our world. Which part of Earth's history blew your mind the most? Was it the microscopic machines making ATP, or how the moon saved our climate? Drop a comment down below and let's discuss. Don't forget to hit that like button, subscribe to the channel, and share this video with a fellow space lover. Until next time, keep looking up